Hello friends, so today we are going to solve some questions, and these questions are from the year 2004. There are two questions from 2004 and one from 2005 and another one from 2006. So there are total of 4 questions. So in the first question, which was asked in the year 2004, it says that an electron moving with the speed u along a positive x-axis at y is equal to 0 enter a region of uniform magnetic field B is equal to minus B naught K unit vector, which exists to the right of y-axis. The electron exits from the region after some time with the speed v at the coordinate y. Then we have to find out what will be this final exit velocity and what will be the y. So in this case, we are given a figure in which the electron enters with the velocity u, and this is its initial direction of this electron with the u. Okay, so it will be in, we can say, x direction, and magnetic field exists only the right side of y. So we can find out the magnetic force on the moving charge on moving charge, that is given as F is equal to Q B cross B, and here charge Q is of electron, so we can write this as minus E, and we substitute the velocity equation as well as magnetic field. So velocity is in I direction, so which gives us ui, and cross product, and we get this as minus b naught k unit vector, and we can just write it or modify it. We get this as minus eu minus of b naught, and here we have I cross k, sorry, and this gives us eu b naught, and we have our I cross k, and our I cross k is our minus of j, so we get that the force due to magnetic field will be equal to eu b naught and minus of j unit vector. So it means the force will be acting along y-axis, but in negative y-axis rather. So we can say Fp will be along negative y-axis. Therefore, we can just draw an approximate figure for that, and so this is x-axis, and it will try to traverse, the electron will try to traverse the semicircular path in this direction, and its initial velocity is our ui, and exit it says is our v, and v, we have to find out what will be the magnitude of v. So let us try to find out what will be the effect on the speed of the magnetic force. we say effect on speed rather, effect of magnetic field on speed. So the force that will be acting on this particle will be always perpendicular to the velocity. So we know the magnetic force is always perpendicular to our velocity. Therefore, under this condition, no work is done on the particle due to magnetic force, that is of Fv. Thus, we can say that the kinetic energy and the speed of the particle is going to remain constant. Therefore, the kinetic energy and speed of particle will remain constant. Therefore, we can say the exit velocity v will be equal to the entering velocity u. The only difference is, if you want to say direction wise, it will be change in direction now in the negative x-axis. So if you want to see its direction, so here magnitude will be equal to u, but its direction will be along our minus I. That will be only difference in the direction. Next, we have to find out the, you can say y, what happens to the y. And like we just plotted the graph or this partial figure, we said that the electron, because of the force it is experience, or we can say the electron will experience a force along negative y-axis. The electron will experience a force along negative y-axis. Okay. Therefore, we can say the electron will start to curve in the downward direction. Therefore, the electron makes a curve in downward direction, and this curve can be also called as a semicircular curve. Semicircular curve. And from here we can also say that electron will move in a region where y is less than 0. Electron will move in the region where y is less than 0. Therefore, the option is option number D, correct option. Option D is Correct. Now we come to the next question. It was also asked by the year 2004, and it states that a proton and an alpha particle, after being accelerated through same potential difference, enter a uniform magnetic field, the direction of which is perpendicular to their velocities. Find the ratio of radii of circular paths of the two particles. So here we have two particles. One is our proton, let us denote it is by P. So we can write the charge on proton will be over plus E, and mass is, let us suppose, is mp. Next is our alpha particle. Let us denote it by alpha. So we can see charge is our q alpha, and that will be plus 2 times electron, and we have mass, which is our m alpha, will be equal to 4 times mass of proton. And it is said that it is being accelerated through the same potential difference. Accelerated through same potential difference. Let us call that as V. So it means the kinetic energy gained by the particle when accelerated through a potential difference V, we can write the formula that our kinetic energy is equal to charge multiplied by the potential difference. And we can write the same formula for two particles now. First one is for protons. Proton, we can say that kinetic energy for proton will be equal to, we have this as charge multiplied by potential difference, and then it is for alpha particle. And this is k alpha, and that will be equal to 2e multiplied by v, because potential difference is same. And for kinetic energy, our kinetic energy is given as half mv square. Therefore, we can write that our velocity will be equal to 2 times k divided by m and its square root. Once again, we can write the velocity equation for proton as well as alpha particle. So we write velocity of proton will be equal to 2 kinetic energy of proton divided by mass of proton and its square root. We substitute the value of the kinetic energy, that is 2, and mass of proton is our same. And next we can write for, similarly we write for it alpha particle. This is our k alpha divided by mass of alpha particle, its square root. This comes twice into 2 ev divided by 4 times mass of the particle. We can just sort out a little bit, and this 2 goes with 4, and we are left with square root of charge multiplied by potential difference, and we have here mass of proton. Now we have to find out the ratio of their velocities. So we can say velocity for proton divided by velocity for their alpha particle will be equal to, we have here em mp, here should be v, and for proton we have here 2ev and here mp and its square root. All the rest of terms cancel out and this comes as square root of 2. And we are supposed to find out the ratio of the radii, okay, and we found out the ratio of the velocities. So we are interested in radii. So we can say radius of circular path, radius of circular path, if it is given as r, so r will be equal to mass into velocity, charge into magnetic field. And once again we can write this for proton as well as alpha particle. So we can say radius for proton is equal to mass of proton, and we have velocity of proton divided by E and magnetic field, and we can write radius for alpha particle will be equal to mass of alpha, velocity of alpha divided by charge multiplied by magnetic field. And mass of alpha relationship we know is a 4 times mass of proton, and we write velocity of alpha divided by 2eB. 2 goes with this 4 and we get here radius of alpha particle is equal to twice mp v alpha divided by eb. And we also know that our relationship between velocity of proton and velocity of alpha, so if we substitute it, we can write that our radius of alpha particle will be equal to twice mass of proton, and here we can write velocity of proton and square root of 2 and we get EB, and this comes as square root of 2 mass of proton, velocity of proton divided by EB. And finally we find the ratio of alpha to proton. Alpha to proton is equal to, we have here square root of 2 mpvp divided by eb, and here we have mpvp divided by eb. This entire term cancel out and this comes as square root of 2. So this is the ratio of alpha to proton, radii ratio of rather. Next question. This was asked in the year 2005 and it states that a moving coil galvanometer experiences a torque Ki, where I is the current. If n coils of area A each and moment of inertia I is kept in the magnetic field B, then based on this description we have three questions rather. Find K in terms of the given parameters. For a current I, deflection is pi by 2. Find out the torsional constant of the spring. If a charge Q is passed through suddenly through the galvanometer, find out the maximum angle of deflection. So first of all, we are given that torque is given as K multiplied by I. We can say torque tau is equal to K multiplied by I, where this K is our galvanometer constant and I itself is given as current. So K here is galvanometer constant. And if I current is flowing through a coil which is having n number of turns, we can find out what will be the torque due to the magnetic field then. So this was the torque for galvanometer. So let us call this as tau g, and next we find out torque due to magnetic field. Torque due to magnetic field, and right, torque due to magnetic field is our NIAB, and this is our sine of theta. And for maximum torque, theta is above 90 degree, so we can say torque B maximum will be our NIAB. Now we can say, comparing, let us call this as equation number 1 and this as equation number 2. So from equation 1 and 2, from equation 1 and 2, we can write our Ki is equal to NIAB, and this gives us that K is equal to, here I goes with I, and we are left with NAB. So this is the expression for the K. Now we find out the torsional constant when the deflection is pi by 2. Torsion constant when deflection is pi by 2. So when the coil will be deflected by angle suppose phi, when coil deflects by angle phi, because of this we are going to have two torques. And first will be our magnetic torque, that will be our tau magnetic, and it will be our NIAB sine of phi, and second will be the restoring torque, that will be due to spring, and it will be equal to C multiplied by phi, where C is a torsional constant. C is our torsion constant, and it says that at equilibrium, or basically we can say at phi is equal to pi by 2. At phi is equal to pi by 2, we can write this NIAB sine of pi by 2 is equal to C pi by 2, and sine pi by 2 is 1. So we get this as our C will be equal to, we can write this as 2 NABI divided by pi. And we finally come to part C. And in part C, it says that when charge Q is passed suddenly. So therefore you can say that impulse due to charge. Impulse due to charge. We can write it as total impulse torque will be equal to integration tau dt, and we already know that our tau is equal to NIAB, and we also know our current is equal to, or rather we can say dq by dt. Therefore we can write integration tau dt will be equal to NAB integration of I dt, or that we can write integration of dq by dt, and that will be equal to our NAB times q. Okay. And it will also provide an angular momentum. So we can say that impulse provides angular momentum and that is given as L, which is equal to over I times omega, where I is the moment of inertia. And now we can use conservation of energy to find out this particular relationship. So we can say that our conservation of energy, so we have our kinetic energy because of the moment of inertia, that will be equal to half I omega square, and that will be converted into kinetic energy into the spring. You can say is converted into potential energy stored in the spring at maximum deflection. Therefore we can say that our half I omega square is equal to half c theta square and maximum deflection, and we already know the formula that our L is equal to, let me write, our L is equal to I omega, and that will be equal to our NBAQ, so which gives us the omega will be equal to NABQ divided by I. And we can substitute this value of omega, let us call this as equation number 3. So you can say from equation 3 we can write half I, and we have here NABQ, and our I whole square is equal to half c theta square and its maximum. And if we solve it, we can conveniently get our theta maximum will be equal to NABQ, and we have square root of c multiplied by I. Now we come to the final question, and here it is said that it was asked in the year 2006, and it said that which of the following statement is or are true for the given figure. So this is a given figure, and we have long current carrying which is perpendicular and carrying current in the inward direction, and this is a loop, and loop carries a current I2, and this conductor carry a current of I1. And from here we can just draw, we can say, approximate magnetic field lines, and that approximate magnetic field lines will be something like this, in this direction, and it will be also in this direction, and here also will be also in this direction. Okay, concentric circles. So therefore we can, or whether we can say, we also know that the magnetic field from the wire, so we can say magnetic field at a distance r from a long straight wire, from a long straight wire. We can write this as B of r is equal to mu naught I upon 2 pi r, and here current in the wire is given I1, so we can write this I1. And from the figure, we have a arc AB, and let us suppose its radius is r1, and here a small component dl will be parallel to our magnetic field. So dl will be parallel to magnetic field, so this gives us our dl cross b will be equal to 0. Therefore the force FAB, because of this small arc, will be equal to 0. Now we have another arc, that is our CD, arc CD, and it is at radius r2, and similarly we can say that our DL is parallel to B, which gives force due to this DC will be equal to 0. Now we come to the radial segment AD. Third is our radial segment AD, and here our DL is along r unit vector. Therefore we can write our magnetic field B will be equal to mu naught I1 divided by 2 pi r, and our DL cross B is along Z unit vector. So we can find out our FAD will be equal to current I, and here we have R1 to R2, dr and r unit vector, and current is I2. Let me put it I2. We substitute all the relative things and try to integrate. We are going to get this as this is I1 and this will be I2. So mu naught upon 2 pi, and this comes a natural log of R2 divided by R1 and along Z unit vector. And the only difference between this AD and CB will be the, you can say, our unit vector. Therefore we can say that our unit vector The third part, we have the fourth part, we have a radial segment CB, and here DL is along a unit vector R, and similarly we can write that our F CB will equal to minus I1 I2 mu naught upon 2 pi natural log R2 by R1 and Z unit vector. Therefore, net force will be equal to FAD plus FCB. Rest of the forces are already 0. So this summation will be also equal to 0. So there is no net force in the loop. No net force in the loop. But these two forces, FAD and FCB, are, you can say, will produce a torque. So you can say from here that net torque on the loop, and that will be equal to torque is equal to R cross F, and we can say that our FAD is equal to minus F of CB. So because of this, they produce torque. So let us check. Yeah. So they are going to, we can say, net force on the loop is 0. So option number A is correct. And it will be producing a torque that will be in the clockwise direction. So option number C is also correct. So option A and option C are correct. Option A and option C are correct. I think these are the only things which were asked for. Yeah, so these were the things that were asked for. Yeah, so these complete.